Okay. Yeah, well, hello, everyone. Firstly, thank you to the EAGE for inviting me for this talk. And also thank you to everyone in the audience for turning up. So I'm going to be presenting most of the work from my PhD. And this is on characterizing an aquifer for CO2 storage. And we're going to use typical hydrocarbon exploration workflows and data sets, and we're going to repurpose them for CO2 storage. And just before I start, I just want to say a thank you to the other co-authors that are listed here, and also to the data providers, TGS and CGG. So I first wanted to start talking about the scales of exploration. So when we explore for any resource, we first start at a very large scale, and then gradually we decrease the area of interest and increase the level of detail as we remove areas that are either unsuitable for storage or are not in our main focus. And you may have seen this being portrayed in a pyramid or a triangle such as this. And it's the exact same thing for what we do for CO2 storage exploration. So the first stage is aquifer screening. And this is basically where we look at a basin and we assess all the aquifers in there for their suitability to store CO2. So this has been done for most basins around the world. And this is just an example from the CO2 storage atlas for the Norwegian North Sea. And each of these different outlines is an aquifer that was assessed. Because you're including all the aquifers, you're looking at a very large stratigraphic interval. And therefore, you can only really assess the aquifers using average properties. So average porosities, average net to gross, average seal thickness. And then we apply that to the full aquifer, with the end goal of basically saying, these aquifers are okay for storage, or these aquifers have potential for storage, so we move them on to the next stage. And it's in this next stage that this study starts, where we're actually trying to assess the 3D variability of these aquifers, of a single aquifer, sorry. And we do that in two phases. We first look at the containment, and containment is basically making sure that CO2 remains within the aquifer. So we look at it laterally and see the areas where we would expect CO2 to leak, and see the areas where we would be confident that CO2 would be stored. So we assess different things such as seal integrity, overburden migration paths, seal bypass scenarios. And basically the end result is to try and provide a map to show, these are the best areas for containment and these are the worst areas. And then the other thing we have to look at is capacity. So we have to look at the reservoir itself. So porosity distribution, where we have intra-aquifer mudstones, are they baffles or are they barriers to flow? We look for structural closures, and then integrating this with our containment assessment, we're able to highlight the best areas for storage, and then we can look for prospects just within that area. And then after that, we can then go to the final stage of the triangle here, and that is to actually mature these prospects. And we do it in this study through dynamic simulations. So where we inject CO2, we want to look at, how it migrates through the reservoir, the effects of the intra-reservoir mudstones, and overall, we want to see what is the storage capacity. So I'll be taking you through these stages, but just to start with the phase one, so looking at containment and capacity. This is the workflow that we use, and I'll take you through the data set that we used, then go through how we prepared the data ready for the main analysis, and then finally the results. I'll start going through the containment, and then I will move on to the capacity. So this workflow here, this has been tailored towards the aquifer that we're studying, but the different elements can be added or removed depending on three different things. Firstly, the geology that you're looking at. Secondly, the data that you have available. And finally, the amount of time that you have to actually perform the task. So the aquifer that we're focusing on is the Utsira-Skade aquifer in the Norwegian North Sea. And this is an elongated sand body around 450 kilometers long. This map here is just of the Utsira formation, with the air and Skade formations being just below this, but within the limits given here. And you should notice that it's also quite a shallow aquifer. The deepest we actually go to is around 14 to 1500 meters. So this aquifer has actually received a lot of attention in the past, and that's primarily because it is already used for storage at Sleipner, which is down here in the south. And most studies have either focused around this area or they've looked at the full aquifer. So that's where they look at that bottom layer of the pyramid. So these are several studies that have looked at this, and they've given a total storage capacity for the Utsira formation. This is for. And although the numbers are variable because of the different scenarios that they use, they all do not consider stratigraphic variability. And this not only affects the feasibility of storage, but they don't identify where the best areas to actually store CO2 are. And we need an approach to systematically map and assess this variability. And that's where the study that I'm going to be showing you today, that's where that comes in. So in terms of the data set, so we're focusing on the northern part of the aquifer, the northern half. And the limit of our study area is defined by the limits of the broad size seismic survey of the North Viking Graben, which is in this yellow box here. We use 141 exploration wells, mostly from Norway, but then there are a few in this little slither here from the UK. And we also have an interpreted lithology column from TGS through their FASHES map browser tool. We also have an FWI velocity cube, and we use that in the capacity study, but I'll go through that when I come to it, because I'm starting off talking about containment. So before we go on to the main analysis, there's two stages of data preparation. The first was to define our stratigraphic framework. And this is split into the two intervals, the capacity interval, which is the main reservoir, which is formed of the Utsira, air and Skade formation. And it represents part of a prograding deltaic complex coming from the East Shetland platform, which is down here, and then going into the center of the basin. And this seismic line, we can see, is on this red line here. And overlying this is the lower Naust formation, which forms the seal and overburden. And this is two prograding cliniform systems, one from the East Shetland platform, which is this section here, and then one from the Norwegian mainland. And they're interacting in the center of the basin. And we split this seal and overburden interval into 6 separate units, depending on the depositional architecture that we observe. And also we wanted to pick the most laterally continuous and strongest reflections. And the top of our containment interval is the upper regional conformity, which is this green line here. So the other stage to prepare the data was that we wanted to simplify the lithology column from the FMB one. And this was simply because we were focusing on, we had 141 wells, and due to time constraints, we wanted to make well correlations and comparisons easier. So these are the initial TGS lithologies, and we basically just simplified them into mudstone, sandstone, and other. And you can see the percentages here, just for the seal and overburden interval. It was around 99.8% was mudstone or sandstone. So that was the data set and data preparation. I'll now go through the main CO2 storage analysis for the containment interval. And basically, we are assessing elements that contribute towards CO2 staying within the reservoir. So we assess seal internal geometry, we assess sandstone distribution in the containment interval, and sandstone connectivity. And then we augment this with a shallow gas assessment. We don't look at faults simply because there's no faults that we identify going through the seal and overburden. Obviously, this would be a big part for other aquifers. So just wanted to start with looking at the typical scenarios we are looking for when we talk about seal and overburden bypass. So we are focusing on the sandstones, and in particular, where they are and how they connected to both the reservoir and also to each other. And because of this, we split the containment interval into the seal interval and the overburden interval. And the seal interval, you can think of it as your minimum threshold thickness of mudstone that you would need to store CO2. So for example, we use 50 meters here. So basically what we're saying is that we need a mudstone that's 50 meters thick directly above the reservoir for that location for us to be confident of CO2 remaining within the aquifer. And therefore, when there is sandstones within this 50-meter interval, we therefore don't have a mudstone to reach our threshold thickness. So we can imply that we wouldn't be confident of containment. So that's why we study the sandstones, and we look for, for example, if I just go through some of these scenarios, the sandstones can be connected to the reservoir, but then these may pinch out up dip in the overburden interval, or the sandstones may be connected to the reservoir and then they are connected through the full overburden interval, for example, in foreset channels, and these would provide complete migration paths out of the storage complex. We also identify sandstones that are disconnected from the reservoir due to a mudstone in between. So, for example, scenario 7 here, or up in the overburden here, scenario 3. And what we then have to assess is the mudstone. What is its spatial distribution? How does the thickness change? Are there actually areas where the sands are actually in communication? So in order to look at this, we did manual and semi-automated mapping of each of the claniforms, and this formed the foundation for seismic attribute analysis. And we've done this alongside well correlations and well analysis. So now I'll go on to the main elements in detail, the main results. So I've gone through the dataset preparation. So the first element that we look at is seal internal geometry. I didn't mention that in that previous slide, but basically the theory behind this is that where you have dipping stratigraphy above the reservoir, you're going to juxtapose more subunits against the reservoir, and therefore you're going to increase the likelihood of a sandstone being in contact with the reservoir, as opposed to where you have flat-lying stratigraphy, where only a single subunit would be against the reservoir for a given area. So in order to assess this, what we did was we took the top aquifer surface and we raised it 50 meters. So now it is at the top of that seal interval. And we extract amplitudes at this surface. And where we see broad areas of single colors, it means that the surface is slicing through flat-lying or parallel to reservoir claniform bottom sets. Then when we see these areas where we see alternating polarity bands, it means that the surface is slicing through dipping stratigraphy or claniform foresets. So if we do that to the aquifer here on the right, we can see those alternating bands in both the East Shetland platform claniforms and in Norwegian mainland claniforms. And therefore, that's suggesting that we're at the foresets within 50 meters of the top of the aquifer in these sections. If we look slightly further to the north, we can see these broad areas of single colors. And this signifies that we're slicing through parallel to reservoir or claniform bottom sets in these sections. If we overlay the wells on top of this, so this is the sandstone to mudstone percentages of just the seal interval, so just that 50-meter interval. And what we can see is where we have identified the East Shetland platform foresets, they are sand rich, whereas the Norwegian mainland claniforms are sand poor. But that was just an introduction to looking at the sandstones, but we want to look at that in more detail. So we decided to look at the sandstone bodies done on their unit on which they occur in, because we wanted to capture the full depositional system. So we identified sands in each of the 6 units, which I've shown here on this cross section. I'm going to show you the results from the first 3 units, just because these are the most important, because they're closest to the main aquifer. And what I'll show you them as is we see a thickness map of the unit, and then within that we see the sandstone to mudstone percentages for the wells. And using this, we were able to identify the areas of the sand where the sandstone bodies are, and then we were able to go into the seismic and map out these bodies. So this is the results just for the first 3 units. So units 1 here, we see high sand content in and on the slope around the East Shetland platform. In units 1 and in units 2, we see that. And then if you look here in unit 2, we can actually see the outline of a thickness increase, which signifies a sandstone. And we see that in the wells here, signifying a sandstone body. And we can also see another one here in unit 3, slightly smaller and slightly more further north. In terms of in the centre of the basin, the only sandstone we really see is here in unit 3, and that's sourced from the East Shetland platform. So we went through and we mapped out these sandstones using the wells. But in the areas where we had poor well control, we looked at the seismic and looked for seismic geomorphologies. So this is a variance extraction from different clinothems and then a frequency blend. And these are both in the southeastern part of the study area down here. And what we see is submarine fans with clear channel lobe geometries. And these represent distributary feeder systems coming from the shelf. And given their unique response relative to the surrounding, we can infer that they are potentially sandy. And obviously this was done for the full area, but I'm just showing you an example. So then we wanted to, show on a map where the actual sandstones are. So we classified sandstones based on a 3-tier system. So where we had proven sandstones, it's where we could visualize them in wells, and we could also correlate them on the seismic between the well. Probable sandstone is where we had a proven sandstone body, and then we extrapolate it beyond well control. And finally, where we had a possible sandstone, this is where we had a seismic signature or a seismic geomorphology of a feature that we would expect is potentially sandy. However, there is no well penetration. So then we've put this on this map as either solid, cross-hatched, or dotted for each of these. And then it's coloured by the unit of occurrence. So what we can see is most of the sandstones that are proven probable and in the lower units are located on the western side of the aquifer. So the aquifer is in red outline here, and most of the sandstones are on this side. On the eastern side, we do see sandstones, but these are mostly in the higher up units. Yeah. So now we've actually identified the bodies, we wanted the sandstone bodies, we also wanted to look at the connectivity between them. So we look at the connectivity between the reservoir itself, the seal interval sandstones, and the Overburden interval sandstones. And we're not just looking for direct vertical migration, we're looking for migration up the depositional systems. And we identified from the East Shetland platform, from this area up here, we identified channels going down into the Tampen Spur. And in the Tampen Spur region, there's good sandstone connectivity up, and then we could follow the sandstones back up dip through the sediment source, signifying that these would be migration paths for CO2 if injected in these areas. So we also used seismic evidence of shallow gas as a proxy for sandstone connectivity, because the seismic evidence of shallow gas, so if it was gas that we could show gas we thought had migrated into its current place, then those paleo migration pathways could be reused by CO2 during injection. So it's obviously something we wanted to avoid. So we performed a regional gas screening, looking at minimum amplitudes and variance. Minimum amplitudes, we split it up into 2 intervals. So most of the containment interval, which is shown in red, and then we had another one around the upper regional conformity. And the reason for this is that this is an area where a lot of shallow gas is trapped. So we wanted to make sure that that was separate from what we would observe in the clinoforms. And then we showed this on the variance to show different features and also to highlight any if there's any gas chimneys. And there's a lot of interesting features that were highlighted, but all I wanted to talk to you is down here in the south. So this is where I identified those channel lobe systems, submarine fans, which you can see here in the variance. And what we see is that the high minimum amplitudes in the cliniforms themselves in red are quite, they're confined to these systems. And where these cliniforms are truncated by the upper regional conformity, you can see the trend of it here. We see that the shallow gas at the upper regional conformity, or sorry, the high minimum amplitudes that could signify shallow gas, also trend in this location. So therefore, it signifies that gas may have come up the cliniforms and then it's being trapped at the unconformity, and therefore it signifies migration paths. So we did this analysis, and then we wanted to actually put it into a map form, so something that could be used going forward in terms of where is the best and worst areas for containment to help us identify storage sites. So for that, we introduced our containment confidence assessment. And this was a semi-quantitative way of scoring the containment interval, where we assigned scores related to the different features. So where we assign a score of 0, it means it's neutral, so it doesn't affect our confidence in containment. Basically, positive numbers are good. So i.e. in positive numbers, we would be have confidence that CO2 could be stored, and negative numbers is where we would be less than confident that it probably leak from these areas. And I've just brought back this this schematic from near the start just to show how this would score relating to the different units that we use. So the first thing we looked at was seal geometry. So where we have parallel stratigraphy in the seal interval, we assign a score of 0, i.e. we don't see it as good or bad for containment. But where we had that dipping stratigraphy within the seal interval, that reduces our confidence in containment, so we score at -3. So the second element, sandstone presence, the scoring depends on 2 different factors. Firstly, the evidence of sandstones, i.e. if they were possible, proven, or probable. Possible, probable, or proven, i.e. the scoring getting reduced even more of each one. And also whether or not where they're actually in location to the reservoir. So i.e. the ones in the seal interval are obviously a lot more detrimental to storage than ones in the overburden interval. Hence you can see the overburden interval sandstones only reduce our score slightly. So for the main aquifer, we can see that it's on the western side that we have the high negative scores. And by identifying the sandstones, we can also do the inverse and identify where we expect mudstones, where we can see mudstones in the wells and where we can correlate this across on the seismic. So the areas we can see that is up in here in the north east of the study area. And that gives us our positive scores. For the overburden interval, sandstone's a lot more common, and obviously that's because the overburden interval is a lot larger. But like I said, it doesn't reduce our confidence that much because they are disconnected from the main aquifer. But they can be, the reason for these is mostly used when we talk about the connectivity. So we look at connectivity between the 3 intervals: reservoir, seal interval, and overburden interval. So where we have a full connection path between the 3, we assign, reduces our confidence in containment the most. And then when we only have it between the 2, depending on what sort of connection it is, that also reduces our confidence. So then you can see on the schematic, how each area scores differently on each different elements. And the end goal is actually then to basically for each location to sum up the scores to give an overall containment confidence of which shows the lateral variability. So you can see here, how much it varies over quite a short distance. And if we look at the Utsira formation itself, combining all these maps together, we get our overall summary map. And we can see that the worst areas of storage is on the western side. We have really high negatives when they all combine. And the best area for storage is on the northeast, because we have seal interval, we have parallel to reservoir stratigraphy. The seal interval is mudstone dominated. We do have sandstones within the overburden interval, but they're obviously disconnected from the reservoir by the mudstones. They don't actually have any connectivity score. And that gives us, these numbers that we find here. So, we can now use that to identify storage sites. But before we do that, we actually need to assess the reservoir itself, the main aquifer. And we use the same data set and data preparation. So the section here that says both. but then we also introduced the velocity cube. So I'll go through that quickly before going on to the main analysis for the capacity. So we wanted to basically convert the velocity cube into a porosity cube. And we did this by defining a linear function between, or a relationship between porosity and velocity. And we did this using the well data. So we converted the density and sonic logs using simple calculations into the porosity and velocity log. We removed any spurious data, or any spurious data, for example, where we have cavings and stuff. And using this, we were able to basically plot porosity versus velocity. So this is for each different color represents a different well. And just to say, we're looking shallow, like I said, less than about 1,500 meters. So most of the wells in our area didn't contain both logs. In fact, it was only 17 wells that actually did contain both logs that could be used. So yeah, we plotted these against each other, and then we could extract the linear function. And you can see we had an R value of around 0.41, which shows a moderate to fairly strong correlation between the two variables. So we took this function and we basically just applied it directly to the velocity cube, converting it to a porosity cube within our studied interval. And here you can see, when we actually extracted the porosities for the full aquifer. So this is the aquifer average porosity. And you can see that the values range from 29 to 39% across the aquifer. And, this is showing that this is a high porosity sandstone. But you can see that where the actual porosities have been measured down at Sleipner in the south, they also get very high numbers. So it provides confidence that our numbers are within reliable limits. And then if we look at this map, you can see that where we have the highest porosity is around the south. And that's because we're close to the sediment source. We're close to the East Shetland platform. And then as we go deeper into the basin, we become further from the source, and then our porosity reduces. The anomaly to this is this section here, and that's because this is sourced from the Sognefjord region rather than the East Shetland platform down here. If we look on the vertical scale, so if we look at this cross-section, which is running through the aquifer, what we can see is that in the Utsira and Air formation, we have higher porosities relative to the underlying Skade formation. So just to run through quickly our mudstone analysis. So like I said, we want to look at whether or not these are baffles or barriers to flow. And from our containment analysis I showed at the start, I said that our minimum seal thickness threshold was 50 meters. So i.e., we want 50 meters for it to be a barrier to flow rather than a baffle. So we have to apply the same scheme for the intra-aquifer mudstones. So, this is this here is a map of the full aquifer thickness. And each of these pie charts represents the sandstone to mudstone percentage. And the perimeter of the pie chart represents the maximum mudstone thickness encountered within the aquifer. So obviously it's only where we see these green perimeters that we actually have a potential barrier to flow. And just to quickly sum this up, the only area we see this is down here. And this is for the mudstone that separates the Skade formation from the overlying air formation. And therefore, if I just draw you to the attention to this image here, because that could be a barrier to flow, we had to perform a full containment confidence assessment of this mudstone. So again, what I previously showed you, negative scores are bad, positive are good. And we also introduced different elements because it was a slightly different system. So that faulting was also used here. And what you can see is, in fact, most of the mudstone is actually not suitable. It's only this very western margin that could be used to store CO2. And when we talk about, we looked at every seismically resolved mudstone. But just to show you one more, this is the top air formation mudstone. And you can see the thicknesses here of the mudstone are thin, less than 10 meters. And we can also identify channels running through it. So these would have been, looking at the seismic, these signify that these are potentially sandy. and therefore, these would have been mudstone bypass systems if CO2 was to be injected under here. So we only identified, moving on to like the closure analysis, we only identified closures in the underneath the mudstones that we said could be barriers to flow. So that's only underneath the top Skade formation mudstone and underneath, obviously, the top of the aquifer, the mudstone at the top of the aquifer. So we performed a simple fill and spill simulation using 800 random source points. And it's basically, it doesn't take into account reservoir heterogeneity, it's just done off the surface. So it basically injects a fluid and the fluid would migrate up dip until it reached a closure, it filled the closure and then keep spilling until it left the map. So this can show us the largest closures. So here's the 100 largest closure for each top formation, but it also showed us the overall migration pathways. And you can see that for both the Skade and top Utsira formation, the migration pathways are back up towards the East Shetland platform, the source, the sediment source. And it's also, obviously, this is the regional dip, it's going back towards that area. The only exception to that is up here, and that's because, like I said, this is sourced from the Sognefjord region. Therefore, that's why the migration pathways go that way. So we identified the closures. We wanted to work out the static storage capacity. So just using a simple equation. So here is just the effective storage capacity. For each closure, we had a, we could measure individually the GRV, gross rock volume, net to gross, and porosity. And then we used analog data for the CO2 density and the storage efficiency. And we performed the static estimation using two different methods. We first imagined, if you were to inject at the bottom of the closure, you'd fill up all the reservoir. Well, depending on what the heterogeneity of the reservoir, you'd basically use up all the full reservoir thickness, which is what we call FRT capacity. However, if you were to rely on a fill and spill approach, then the CO2 would be coming in from the side, and therefore, you'd mostly only use the closure itself, i.e., from the apex to the spill point. So we call that top to spill point capacity. But before, we didn't want to do that to every closure. We just wanted to do it in the area that was suitable for storage. So we integrated the capacity assessment with the containment assessment, and then we just identified we just identified our prospects within the suitable area. So we had 4 main prospects here. Their storage capacities are shown in these numbers for the full reservoir thickness. We included 2 other prospects within this area. So this is area that it's a suitable depth, but these prospects have a negative containment confidence score. The reason we've included them here is just to say that we've used that seal interval thickness of 50 meters, but we've kind of picked an arbitrary number there. As more work is done on seal integrity and looking at mudstone geomechanics, this number, you could work out that you actually only need, say, a 30 or 20 meter mudstone for this aquifer to actually store CO2, and therefore by bringing the thickness of the seal interval down, it may introduce more of the aquifer as suitable for storage. And that's why, although they're not suitable here right now, if the containment confidence system was done again, but with these new limits, they might be suitable. But the prospects that we currently have are suitable are these ones here. So there's 4 prospects, and you can see that prospect 5, this one here, the largest one, this is a lot larger than any of the others. So that was that was basically the regional assessment. We identified the best and worst areas for storage, and we identified prospects within the best area. We now move up to the second phase, which I'll run through quickly, which was to actually inject or simulate injection of CO2 into the aquifer. And for this, we had to make a reservoir model. So we had to bring the area right down to just this red box. And what it includes is both the prospects, and you can also see it includes these smaller closures that on their own are not suitable for storage due to their size. So that's here. So these are the 2 prospects, and then these are the 4 extra closures. And we did a further, more detailed geological assessment just around this area. And we identified 3 laterally extensive intra-formational mudstones. You can see in this well here, and they went across the full area. So therefore, when it came to us building our reservoir model, we put in these 3 mudstones, which gave us in the end 4 different Utsira sandstone zones, and then there's different layers in each of these. One thing I should say is, you can see that there's quite mounded the topography here of this base aquifer surface. So the BU means base Utsira, and the sandstones lap onto these mounds. And therefore, when you look at the sandstone distribution between the 4 zones, which is down here, zone 1 and 2, the sands are quite isolated because they're only in between the mounds. And then as deposition continues, the mounds get buried, and zones 3 and 4, the sandstones are a lot more laterally extensive. So for our simulation, we also used 6 different well locations, so 3 up here and then 3 in the main prospect. And then for our reservoir simulations, we'd run a load of different tests, and we used a migration simulator, and that relied on invasion percolation physics. And we used an injection rate of 1 million tons of CO2 a year. And for our prospect 5, i.e. the large prospect, we injected the full reservoir thickness storage capacity, which was 32 million tons. That was our initial starting injected amount. And then we ran the simulations for 50 years after injection stops, just to see how CO2 would migrate. And we ran a series of tests, but what I'm going to show you is just 2 of them. Firstly, we wanted to compare the dynamic simulation to the static numbers for the full reservoir thickness. And therefore, we injected CO2 near the base of the reservoir. And we also wanted to see the effect of the intraformational mudstones, because by changing their properties, how did it change their storage capacity? And then the second test we ran was to inject CO2 near the top of the reservoir, and then we wanted to be able to compare it to the top spill point capacity estimations. So this here is for the first test, and what you're seeing is the main prospect, which is the black outline. This is the map view, and then each of these different colours represents the top zone plume spread at the end of the simulation for each of the zones, so zone 1, 2, 3, and 4. And this first one was where we had low threshold pressures for the mudstones. So i.e. a high, only a small amount of CO2 would build up as a column before it would break through the mudstone. And you can see just by the first 3 layers how confined they are. And on the cross section here, that basically it broke through the mudstone straight away before filling up the top. If we increased the threshold pressure of the mudstones, then we get a larger CO2 plume underneath each of the mudstones, and therefore, when it finally breaks through, there's less CO2 that actually fills the structure. If we increased the threshold pressure even more, so now a larger column can build up, we see that the plume is a lot larger, and in fact it doesn't actually break after injecting the 32 million tons. It doesn't actually break through the final mudstone. And what I should say just about this number, this is still within the limits of what could be found there. It's it still is viable. So we increased the actual injection amount to 70 million tons, and once we reach that, then we filled the structure. Any further CO2 and it would leak out. But what this highlights is that how important understanding those threshold pressures of the mudstone actually are, to how much it increases the capacity. We did actually increase it even more than this, but once you increase it even further, which again still could still be realistic, but it's on the upper end of it, then we saw that at the zone 1, so the red one, it actually migrated beyond the structure. And therefore, that's something we want to avoid, because then it doesn't use up any of the overlying aquifer. It would go outside of our control. So then the other study was to actually inject CO2 near the top of the aquifer. So now we're injecting above the interformational mudstones, and we want to see, how much CO2 can be stored that way. And just if I start with the ones to the right, we changed the well location just to see the invasion sequence, but it showed that we could store 34 million tons in the top to spill points of the prospect. But then we also looked at injecting in prospects further back or closures further back and then letting it spill into the main structure, because this would increase the total storage capacity from a single well. So we injected in well 1, well 2, this section here should be here, but I just separated them just to, for ease, and then well 3. And in well 1, what you see is that we fill up this small closure, it spills into the second one and into the third. Unfortunately, though, it then spills out. It doesn't actually spill into the main prospect. However, despite this, even though these closures were too small on their own, we are seeing that actually with a single well, you still do get quite a large capacity by spilling, using 3 of these structures at once. For wells 2 and 3, after filling the structure, they then spilled into using the same migration path to reach prospect 5. So if we take well 3, if we were to inject here, we'd be able to store 9 million tons, as well as, the 34 million tons in the closure itself, which increases, the total storage capacity from a single well. So last slide before I go to the summary, and it's just to say, you would notice that there's a difference in between the static calculation, so this is for prospect 5 of 32 and 18 million tons, and the dynamic simulation, where we saw 36 to 70, depending on the threshold pressure, and 34 million tons. And both estimations, obviously the dynamics a lot more advanced, but they both have the same gross volume, the same net to gross, and the same, similar, of M3, and CO2 density. The big difference is this storage efficiency. And this is a number that's used that, I think there's a lot more work that could be done on this, especially to use it for local calibration, because the current range in acceptable values, is 2 to 10% for the full reservoir thickness, or 3 to 40% for the top to spill point. And we originally used, middle of these, and you can see that from our dynamic simulation, we actually are reaching the upper end of this. So, we would have had to have used storage capacities of this and this, i.e. the top end. So I think a lot more work can be done on this to make it viable for static calculations in the future, to really reduce that uncertainty of how much CO2 can actually be stored in these structures. So, just to summarize, hopefully I've shown you how we characterize aquifers, identify the best and worst areas. We can then look for prospects, and then we can mature those prospects. I've used typical exploration workflows and data, and therefore it shows, the transferability skills of geoscientists, making the switch between the two. And finally, I just want to say that, geological heterogeneity is very important to include. We see a lot of capacity estimations for aquifers, really high numbers. And once you include that geological heterogeneity, it really brings down, how much of the aquifer is actually suitable for storage. So yeah, thank you for the talk. Thank you for listening. And if you want to ask any questions, feel free. But if you want to know even further detail, you're welcome to message me. Or 3 of the studies are completed, are published. Basically all of phase 1, and the phase 2 study is in preparation. So yeah, thank you for listening. If you have any questions.
Thank you very much for this nice presentation, Chris.